So we have a queue of records, and some slots at the beginning are filled, and new record goes into the slot N, and we have some producer threads and some consumer threads. Consumer can read the slots that are done, full, and producers have to produce new records into the slots that are empty. There are multiple producer threads, there are multiple consumer threads, nothing gets deleted here. We'll have enough trouble without, so this isn't like really a full queue. Nothing gets dequeued yet. We'll have enough trouble with that. So this is what it looks like. Multiple producers are all competing for for the slot to put the next record. Multiple consumers are all reading. Producers could also be consumers. Producers may need the old records in order to construct the new ones. Well, before we used to use those things called locks. So when we used locks, life looked something like this. The producer would take a lock, store, get the count, current value of the top of the queue, store the record in that slot, and increment the count, and unlock. The consumer would take a lock, take the count, consume all the record it needs, and unlock. See the problem here. There is one big lock. Consumer basically locks the entire queue, and while it's scanning all the N records. While that's happening, nobody can get anything done. Okay, we want to do better than that. So lock-free is the same thing, but without the locks. How many race conditions are there? Okay, who sees race conditions? Okay, just shout it out. Okay. Yep. Sorry? Yeah, there is a race condition for increment. There is a race condition for reading, writing N. Yes, anything else? Write to the same record multiple times. Anything else? Consume record that hasn't been written yet. Okay, well, that's enough for, there are more, but that's enough to make it not work. Okay, lock-free queue without atomics. What kind of lock-free queue is that? Let's put atomics in place. There is only one atomic here, really, the count. Okay, now we have atomics. Must be correct. How many races now? All the same ones, yep. I haven't really changed anything, okay? So the important point to take home, lock-free programs in particular, in general true for all concurrent programs, for lock-free programming it's particularly important. Think in terms of atomic transactions. Okay, let's separate our problems. Let's first focus on the producers. So let's focus on the part where producers are competing for the same slot. And the second part is where consumers have to avoid reading things that haven't been constructed yet. Okay, producer problem first. Even on the producer side, we have a race. Several, in fact. Now, here is the tool, the workhorse of lock-free programming. I have to introduce this, any talk on lock-free programming has to have this. And this really is the primary tool of lock-free programming. There is a proof that any algorithm can be done with this in a lock-free manner. Compare and swap. What's compare and swap? If you have an atomic variable and you do a compare and swap on it, it atomically performs the following transaction. Compare and swap takes the old value and the new value. Now, what do I mean by the old value? It's the expected old value. If what's really there is what I think is there, is in the old value, then the new value gets written in, overwriting the old value, and the new value gets returned. If, however, the variable changed, if what I think is the old value isn't really the old value, then nothing gets done, and the current value gets returned. And all of this happens atomically. So it's a read, compare, write, and all of this is done atomically, non-interruptibly. This whole thing is one hardware instruction. If we have this, then this is the standard compare and swap idiom. read the current value from our shared atomic variable, compute whatever you need to compute, assuming that that's the value, and try to swap it in atomically, hoping that the value hasn't changed. If the value has changed, somebody else has updated it. And we have to throw away everything we have done and start all over again. Read it again, read the new old value, compute again, and try to commit it. But if nothing has changed, if the value hasn't changed, we will update it to the new one. In our case, we increment it by 1. And we have succeeded. Our result of our computations has been committed into the queue.
Excuse me, is that a typo in the last line of the slide? Should it be not equal old n plus 1?
Yes, sorry. Yeah, n is the global static variable. Yeah, should be not equal old n plus 1. It returns whatever is currently there.
The successful one should return the old value, the assertion, right?
Well, okay, you can actually have it both ways, and you can always determine. You can always. No, I think I'm sorry. You're right. It should return the old one. So you can determine if it changed or not. Yes, you're right. It should return the old one. You're correct. So if it returns the old one, so you know that if it changed, you got back not what you expected. You're correct. Okay, so this is how you do the queue using compare and swap. And again, the same typo. Sorry, this should be old n on the left side of the swap. Nah, the mouse doesn't work. That n plus 1 should be old n. Sorry. Okay, so we compute the new record. We don't store it. We just prepare it. We try to increment n with a compare and swap. If nobody incremented n while we were building up the record, then the slot n is ours because we committed, successfully wrote n plus 1 into the slot, and we can copy the new record into that slot at our leisure. If somebody changed n while we were building the new record, we have to start all over again. That solves only the producer half. It doesn't solve the consumer half, only the producer half. Okay, this actually works. We kind of simplified the problem a lot. We created a black hole queue. Records go in, records don't go out. Now, that's one interesting problem. There is no, which means the problem is we don't actually know when the records are ready to read. Because the producer, after it reserved the slot, will start copying the record slowly at its leisure. The consumer has to know when that process has finished. Okay, that's half of the problem. The other half, that code looks a lot like a lock. We're basically looping on a variable, and until that variable comes up in an expected state, we can't go forward. What's a lock? Lock fundamentally is we have a flag. If the flag is 1, you loop until it becomes 0. If the flag is 0, you go. That's basically how the locks are implemented. Herb Sutter is even wiser than we think. Think about this for a second. On the overpass, 2 cars still cannot enter the highway at exactly the same time. Well, they can, but you have a race condition when that happens. Under normal operations, the cars still enter at different times. So what's really the difference between lock-free and locked? In lock-free, cars enter the highway really one at a time. They just merge from the overpass. In locked, cars enter the intersection, one at a time. So here's our same thing. Here's our cast loop, and I copy-pasted it, of course, with the same typo everywhere. Looks a lot like a lock. Well, it's faster. I mean, highway overpass, has a lock essentially. Cars don't occupy the same place on the road, two of them. But is it only about high performance? The answer is to a degree, yes. Lock is a much coarse granularity, just like the traffic headlights, switches much less frequently than the cars can when they enter from the highway ramp. So lock is very coarse granularity. Lock-free is really on a single instruction granularity. Is that all? Well, let's explore this a little further. Here is the simplest possible lock. Atomic exchange is a kind of primitive variant of compare and swap. You can implement it using compare and swap. What it does is it atomically stores, it doesn't do a comparison. It just atomically stores whatever you give it and gives you back what was there. So there is no old value and new value, there is just the new value. You can, if you don't have, some CPUs have that as an instruction and maybe faster than compare and swap. If not, you can implement it using compare and swap. So this is what's called a spin lock. It's a busy wait. This is like the simplest possible lock. We try to atomically store, well, you don't try to. Atomic exchange always succeeds. But you atomically store 1. You get back the old value. If it was already 1, which means you haven't really changed anything, you have to spin. But if it was 0, it means you were the first one who stored the 1 in there. So it was 0, means it was unlocked. You are the first thread who put 1 in there. Everybody else will now see 1, but you got 0 as an old value. You can proceed. Okay, so what's the difference between that spin lock and the compare and swap loop? They use a slightly different instruction, but that's unimportant. Atomic exchange and compare and swap are very similar. In both cases, you're looping on an atomic instruction until it returns the value that you expect. They seem very similar. We have to look closer at the differences between different kinds of concurrent programs. There are wait-free programs, and I think, Michael, are you talking about it in more details? A wait-free? Yeah. So Michael will cover it in a lot more detail. So very brief introduction. Wait-free programs, basically no thread waits for another. So each thread just keeps executing its instructions and never waits for anybody. At all times, all threads make progress. Lock-free, programs without locks. But the important part is you have a guarantee that at least one thread is making progress. So of all the threads looping on the compare and swap, one of them will get the old value that it expects, will go out of the loop. Everybody else will go on the second iteration. There is a rarely used category of abstraction-free programs. Now, log-based programs aren't guaranteed to make any progress. Why would log-based programs not make any progress? Well, we'll see several reasons in a moment. Now, log-based programs have one redeeming feature. They're a lot simpler. Part of knowing how to write log-free programs is knowing when not to write log-free programs. The worst problem with logs. Okay, who have seen this before? In their own code. In the code of other people you had to debug. Okay, what's going on here? If the timing is exactly unfortunate, deadlock. If the timing is exactly unfortunate, well, actually here for any timing, doesn't matter what the timing is. Thread A gets a lock, thread B gets, the timing has to be unfortunate. Thread A gets a lock, thread 2 gets a B lock. Now each of them wants the second lock, but they're not giving up the first one, which means neither of them is going to get the second lock, they're both stalled. And they're going to be stalled forever. Okay, we're going to be smart about it. We have this thing called wait lock. We're going to detect that we're waiting forever and not wait forever and release the locks. And when we release the locks, hopefully the other thread will get 2 locks that it needs and will go through. Either that, or you will get into this bounce where you always swap the log. You hold A here, B here, A here, and you always swap it like this forever. That's called live lock. Okay, let's. How are we doing on time? Let's ignore priority inversion. Convoying is actually an interesting one. This is a kind of similar to serialization, but if you have tools like what Scott was showing, where it shows you the timeline, you can visualize basically what your threads are doing. You can notice that the tasks on two threads kind of go like like cars on the road, or like cars like railroad cars, just follow one after the other. And the reason is you got the first lock, did your job, unlocked that, got the second lock, went to the second job, the other thread got the first lock, started doing his job. So you have this basically two parallel executions like this, completely serialized. The first thread that gets to the first lock just zips through all of the locks, doing its tasks one at a time. Okay, why would you write such a stupid code with deadlocks? Well, that's one way. You don't actually know that you're writing stupid code with deadlocks. You're just calling functions. You're calling the same lock on the same thread twice, guaranteed way to deadlock. Signals. If you have to handle signals. Signals are asynchronous, happen anywhere, including possibly while you're holding locks. If you are on Linux, your favorite lock here would be the malloc lock. You're inside malloc, you get interrupted by a signal, you go into a signal handler and you try to allocate memory. Bad idea. You shouldn't be allocating memory in a signal handler. Again, you know that you shouldn't be allocating memory in a signal handler. You do it indirectly. You call printf. Shared memory. Shared memory is an interesting case. Of course, normally you know whether you're using shared memory or not, but if you do, this is what happens to you. You have a mutex sitting in a shared memory. Mutex is actually a fairly complex object. It has a flag and a pointer to some shared state, where is the list of the processes waiting on that mutex and some other stuff. I mean, threads waiting on that mutex. Well, the pointer may be in the shared memory, the state isn't, which means your other process has no access to it. It dereferences the pointer. That pointer in the address space of the second process, that pointer points to anything except the data you want. Okay. Spinlog doesn't have that problem. Spinlog doesn't have secondary state, just that flag and that's it. Spinlog has a slightly different problem. If the process dies without releasing the spinlog, the other process is going to wait forever. Finally, performance. It's listed last for a reason. The reason is it's not always better in the case of log-free programs. And second, log-based isn't always mutex-based. There are other logs that are faster, cheaper logs. We'll come back to that. So as a take-home point, another one, so we studied about the memory order. Know the danger of logs, know how to avoid them. Switching to log-free is only one of the possible ways to avoid them. If you understand what the problem with logs you have and what you're trying to solve, there may be a simpler way to resolve that problem without going log-free. Okay, practical problems with logs. I don't have priority threads in my case. I just want the result as fast as possible. I don't care in which order it's done as long as it's done. Yeah, the thread holding a mutex can be suspended by the OS for an hour, in theory. How likely is it to happen? Not likely. If I have a lock protecting atomic transaction and the user cannot inject his own code using locks into the middle of that, you cannot have a deadlock on that lock. I usually know if my memory is shared. I have to allocate it differently. In real life, at least 90% of the time, you're writing log-free code for performance. There is a special case in some cases, log-free code may actually be simpler. Okay, getting rid of the logs doesn't automatically make it faster. Here is a simple example. I want to increment 2 integers and I want to do it atomically. How do I do this? On some CPUs, there is a 128-bit compare and swap. Even if you have it, it's very slow. There is a really clever algorithm with compare and swap in the 3rd integer that I'm not going to show you. I mean, you can look it up. It's really clever. It's not particularly fast. Do it under the spin lock, which is a variant of that. Spin lock is the 3rd integer. Or you can use one of the integers that you have as a spin lock. For example, if you don't normally get 0, you can use that one of the integers to drop it to 0 as a sign that the whole thing is locked. Well, even faster is to not atomically increment 2 64-bit integers at the same time. How can you do that? This is the first time we come to a difference of application programming versus library programming. You know, people say, well, this is targeted at library developers, this is targeted at application developers. They mean different things. So I need to clarify what specifically I mean when I talk about library versus applications, because some of you who write libraries may fall on the application side in my terminology. If you are an STL developer, you have to be very generic. You can make very few assumptions. In your practical application, you can often make a lot of simplifying assumption about this particular application that you're working on right now. I need to implement 2 integers, which in general are 64-bit. In my particular application, they're counts of some sort. Do they really get that large? Maybe they don't. Maybe I can fit them into a single 64-bit by dividing the word into 2 halves. Not necessarily right in the middle, maybe 8 bits and 48 bits. If the limit is exceeded, if I allocated 8 bits to one integer and 48 to the other, and I went over 8 bits, can I deal with this somehow? Maybe it's a counter and I can just leak some memory, and it happens so infrequently that I'll leak a little bit of memory. Maybe it's a shared pointer counter. I'll leak a little bit of memory, but it happens so infrequently that I'm okay with that. In a given hardware and software, can I steal any bits from somewhere? Again, you're writing an STL container, you have to assume that you will be given a pointer to char. I'm writing my own container. It stores these structs. The structs begin with unsigned long. That's going to be 8-byte aligned on a 64-bit architecture. 3 bits and I can steal from a pointer. I have to put them back before using it as a pointer. I mean, I have to put them back as 0. But I can store 3 bits of information in a pointer. I just have to do an extra bitwise operation to actually use it as a pointer. I am on x86 on Linux. 64-bit machine, it's not 64-bit. They lied to you. The address bus is only 48 bits. The top 16 bits of the pointer are either all 0 or all 1, depending whether you're in a kernel space or in a user space, and you can tell where you are from the 48-bit. As long as you put them back to where they should be, you can store anything you want on there. Again, can't make that assumption if you are writing a generic library. If you're writing a specific application for a specific platform or a subset of platforms, often you can. So this ability to make, is there a question there? You had a question? No? Okay. So to me, the distinguishing feature of application programming versus library programming is this ability to make these simplifying assumptions. So before you jump into log-free, think of, basically don't write the generic log-free case. Think of what, in your application, what simplifying assumptions you could make to share less data. Don't share 2 64-bit atomic words if you can actually combine them into one for your particular application. Maybe you can use a spin lock. If you have to go log-free, now let's assume you have to go log-free. You narrow down your design. You avoid writing the very generic design. If you're writing STL, you can't do that. Okay, now you have to write something log-free. Don't write log-free algorithms, write log-free data structures. right? So design lock-free data structures if you have to do it. Well, let's go back to our lock-free data structure. We still have this, we solved the producer problem, haven't solved the consumer problem. What's the consumer problem? That the producers, they have an arbitration mechanism for their slot where they put new records. Then they go and fill the old records, but some of the old records are incomplete at any given time. Consumers have to know. Very hard to do in a general case. There are many special cases where it's actually easier to do. Here is the simplest one. Let's say our records are actually numbers. Well, maybe long max is not a valid number from the point of view of application. Or maybe 0 is not a valid number. Okay, let's initialize all the memory to 0 or to long max. Let's say to 0. And when the producer is writing the record, which is in our case just one integer into the slot, it'll atomically write the non-zero value. The consumer now knows which records have been initialized, which haven't. If you have 0, it hasn't been initialized. So producer, the very last thing it does, so we already saw how it grabs the slot. It grabs the slot with the compare and swap. And then when it's ready to fill the slot, it uses a, well, in our case, it's a no barrier store because it's just that number. We don't use that number as an index anywhere else, but it's an atomic store. The consumer now, the consumer has to use acquire load on the counter because we save the counter with a release store. That's what guarantees that all the writes into the elements of the array are visible before we updated the counter. And then it can just do no barrier load on the record. As long as there is 0, the record hasn't been initialized. Okay, I was asked a question during the break, how do you prove that these programs are correct? You try to reduce them to something that is easy to reason about, easy to explain. Well, you don't often store just numbers. Here is some record. How would we know if that thing is ready to read? Well, let's say the count cannot be 0 in a fully initialized record. Okay, the problem is reduced to the previous problem. We have seen this before. Make the count atomic count, initialize everything, and the count last with the release store now, because every time you say initialize something last, that's a release store. And I'm oversimplifying because there are other memory barriers, but for the purposes of this talk, it's a release barrier. You can hide this release barrier into the constructor. So the constructor initializes everything inside the object. The very last thing the constructor does is the release store in the count. The consumer now spins on the count. If the count is 0, don't touch the rest of the data. It isn't ready yet. If the count is not 0, you have to read it with an acquire load. Oh, I'm sorry. I need to spin the slide. Okay. You have to read the count with an acquire load. But if you got non-zero, the record has been initialized, and the release store guarantees that the update to the count is the very last thing that will happen. Okay, what if there is no natural flag in the record that tells you that the record is ready? No count, no invalid value that doesn't normally happen. Well, you could add one. You could just add an integer. Or you could fall back on the old computer science idiom and add another level of indirection. Now our queue stores pointers to records. And null would be an invalid value of the pointer, uninitialized. Records now are basically produce only. You put stuff in, you get stuff out, but only through the pointers. Remember that black hole queue that was totally useless? You would never do such a thing in real life. Well, here it is. The bottom half is that black hole queue, because the consumers don't access it directly through the count of elements in the queue. They access it through the pointers that are published by the producers with a release barrier. So, and the top part is, of course, that thing we just looked at, where the records pointers do have an invalid value that we use as an initial value. Very important. Don't try to write generic lock-free code. It's really hard. Try to solve the problem that you need to solve. Okay. Take every advantage of the simplifying assumptions. Well, this isn't really a queue. We are not dequeuing anything. The problem is generic lock-free queue is really hard to write. I think at the last CppCon, somebody was showing generic lock-free queue, and toward the end of the talk, they still haven't quite got all of it working. Because it's really hard. I mean, it's possible. I have written it, to benchmark it for this talk. There is a lot of corner cases you have to consider. What's worse, it's not always faster. And the whole reason we did this is because we wanted speed. Okay. What's the problem? Well, we have to handle all these special cases. When the queue is, so the queue from which you dequeue will have two counts. This is where you add, this is where you remove. What happens when removing runs into the where you add? Your queue is empty. If you just go atomic increment, your tail of the queue will run past the head. Have to handle that case specially. What happens when you run out of memory? When you keep adding things and not taking them out, eventually you'll fill all your memory. How do you handle that? You have to handle all of these cases. In generic queue. In a specific one, maybe you don't. All right, let's look at why the generic queue actually ends up being not so fast as you would hope. What limits, in general, the performance of the concurrent program? But specifically, what in the synchronization? Yes, if you actually have idle threads. If you have to idle some of your threads, then serialization limits it. But even if you don't idle anything, what limits? Let's say everything runs everything is busy. Everything. Very close. In a little bit more general, data sharing. I'll give you a simple example. This should be enough to convince you. I have a single integer variable, and I am incrementing it using atomic increment. And I measure, this is done well, this is done on a fairly large machine because I actually did have 128 cores on that machine. Okay, so the middle column is shared. They're all incrementing the same integer, all threads. And the right column is not shared. Each thread has its own integer and was incrementing it. Well, for one thread, there is a difference between just plain increment and atomic increment. Even for one thread, only 3x. Now, for multiple threads, if you have one integer, each thread incrementing its own, it starts to scale. You get more integers incremented per nanosecond, because if you have two threads, you get two integers incremented and so on. If you're incrementing the same integer, it actually gets slower. I'm not sure what happens toward the end. The machine has weird memory banks architecture, so the timing if you engage all 128 cores, the timing is kind of weird on that machine. Now, it scales, but it doesn't, like what happens, why doesn't it scale? You see that even the one for non-shared access is actually kind of stops scaling. I don't get, when I have 128 threads, it's not running 128 times faster. Why not? Well, if I didn't have any synchronization, I would just write from the CPU to the local cache. If I have to worry about synchronization, I have to know, okay, on x86, 3 levels of caches. L1, L2, L3, and then the main memory. If you have to have synchronization, you establish the coherency between all of these caches, and that goes all the way down to main memory. Well, and there is some arbitration involved, and that's where the cache coherency is between the caches of different CPUs. How fast is that? Let's measure. Rule number 1 of performance. Don't guess it, measure it. Okay. Fairly standard memory benchmarks. I'm going to write its chunk of memory of this, this size on the bottom, that many kilobytes, and measure how many megabytes, the vertical axis is megabytes per second. So on the left is L1 cache, and the drop is where I go out of L1 cache. Then the next drop is where I exceed the L2 cache, exceed L3 cache. The throughput on the right is the speed of the main RAM, about 5x. Now that was for one thread. Let's try the same for 2 threads or 4 threads. Well, for L1 cache, there is a lot of noise in the measurement, but kind of I get the same speed. For L2 cache, for 2 threads, I get the same. For 4 threads, on this machine, L2 cache is shared between 2 cores. So for 2 threads, they're running on different cores. They're using different L2 caches, so you get full throughput of two separate L2 caches. For 4 threads, they're already starting to hit the same. 2 threads, in pairs, they're starting to hit the same L2 cache. L3 cache, you kind of get less and less of it, and then on the main memory, you get slower and slower speed. Let's multiply it by the number of threads, so we know the total memory throughput. What's the memory throughput from all the cores writing and reading? Well, this is writing all at once. Well, if we're doing L1 cache, 4 times more than for 1 core. On L2 cache, not quite. L3 cache depends. You basically effectively have less L3 cache. The drop occurs at a smaller size, so it's like you divided the L3 cache between instead of 8 meg, you get 1/2 of 8 meg or 1/4 of 8 meg. On main memory, 1 thread, you go from 1 thread to 2 threads, it almost doubles. You go from 2 threads to 4 thread, nothing happens. 2 threads writing at full speed saturated the memory bus. Fully. Now, this is, of course, they're doing nothing else but writing into memory. Your program hopefully does some computing also. But computing is fast, writing is slow. You're not, if you have a memory-bound program, you're actually not that far. You may be in a program that does, half computer, like reads a memory word, does 1 or 2 operations, writes it back. 4 threads will probably still be faster than 2 threads, but 8 threads will saturate the memory bus. So data sharing is expensive. Data sharing, the true data sharing of a single atomic variable by multiple threads is really expensive. Even competing for memory gets quite expensive if you have enough threads. That's, by the way, why synchronized access is expensive. You have to write, if you're doing synchronized access, you have a shared variable. How do you do synchronization between threads? You have to have at least one shared variable that everybody has to read and write and agree on what the value is. That costs you. Why do logs cost you more? Protecting shared data with a log costs you more. Inside the log, there has to be another shared variable. In addition to whatever you're protecting with the log inside has at least one more shared variable. Otherwise, logs cannot work. You have to have at least one flag that everybody agrees whether it's up or down. So for that reason alone, if for nothing else, logs will be more expensive. If you want performance, and that's the reason you're contemplating to going to log-free, first minimize your data sharing. Know exactly what is shared and try to share as little data as possible. Overhead of data sharing depends on how much data you're sharing. Mutex are complex things. Yes?
So would that advice still apply if you have locks? Like you should still minimize the amount of data sharing?
Yes, absolutely true. You should always minimize the data that you're sharing. However, if you're comparing logs with no logs, there is, by definition, some more data being shared inside those logs. So for that reason, if you are basically bound by the sharing of these variables, logs will always lose. But there is a flip side to that. Let's say I have a queue, absolutely generic log-free queue. Well, I know how to implement it with 3 independent shared variables. Maybe there is a way better, but I know how to do it with 3. Or I could have one single spin lock, which is a one integer, and I can share that. I tested on a wide, I'll have the slide, I tested on a wide range of machines. A generic lock-free queue on most machines is not faster than an STL queue protected by a spin lock because of how many variables you have to share. So that's actually getting a little ahead of myself. The last bullet on the slide. If in order to guarantee, why do lock-free programs end up with multiple variables being shared? Because that's what it takes to establish memory ordering. This is like a counter or a pointer to something which guarantees that all this data has been written before we update it and so on. So head of the queue, tail of the queue, that's 2. And in a generic queue, turns out you need another one. You need like a writer's view of the tail and the reader's view of the tail, so you end up with a 3. At least I don't know a way to do it with less. Maybe somebody does. So now you have 3 independent atomic variables versus 1 with a spin lock. Not obvious who wins. Okay, so yeah, I got a little ahead of myself with that question, but so the experiment that I have done, and I really wanted to show you the chart, and I really wanted to make it a bar chart, and all the bars were of random heights, so that didn't work. And I really wanted to make then a scatter plot, and it looked like results of a drunk redneck party with a shotgun. So that didn't really work. Results were utterly inconsistent. I'm comparing a true generic lock-free queue with a spin-locked wrapper around STL queue. Depends on the hardware, depends on the processor architecture, depends on how many CPUs the machine has, depends on the access patterns. Do you enqueue more, dequeue more? How often is the queue empty, and so on. But what is consistently true is that if you have special case, if you can take advantage of your application restrictions, you can always get ahead. If you know, for example, how many elements maximum can be in the queue, that's enough to write a very efficient queue. Much more efficient than the general case. If you have only one producer thread, multiple consumer thread, or one consumer thread, multiple producer threads, that's enough. You go down from 3 shared variables to 2 or 1, depending on which case it is. Very different implementations in each of the cases. So you may have to do 3 different implementations, but well worth it in terms of performance. Well, I promised you this question about the queue. So what exactly is a thread-safe queue? Well, we know what a queue is. Oh, of course. What's a queue? Queue has, well, let's look at STD queue. Front, push, pop, empty. STD queue is not thread safe. Let's put a lock around every method and make it thread safe. Push is fine. Put a lock around push. Push is now thread safe. What about pop? Well, this is how you read from an STD queue. You check if it's empty, you get the front, and you pop it. That's the interface you provided. Each member function is a thread safe. Not empty right now. Oops, now it's empty. What happens if you pop an empty? Why is it now empty? Because another thread came in and popped it while you weren't looking. What happens if you pop an empty queue? Sorry? Well, if you're with debug exceptions, undefined behavior in general. Okay. What's the problem here? The problem is a thread-safe data structure, if it's internally thread-safe, whether it's with locks or without locks, can at best guarantee that every member function call is an atomic transaction. That's the best it can give you. It can't do anything between the member functions calls because who knows what the client does between. Which means those atomic transactions that are provided by the thread-safe member functions have to be useful in a concurrent environment. Empty, pop, and front are not useful in this environment. This is the wrong interface for a thread-safe queue. What you need is something like this. Pop So you need to atomically pop if it's there. If it's not there, you need to be notified that it's not there, that the queue is empty, but not fail. There are several, I give you 2 examples. One is you return the element and the Boolean. The other one, you return the pair. There are other ways. You can come up with many interfaces, but you have to have that atomic interface which combines empty, front, and pop in a single transaction. Okay, so very important point, thread-safe data structures they cannot be done with arbitrary interface. They have to have the right interface so that the functions they provide in their interface are useful as transactions. STDQ in particular does not have that interface. So if you design in terms of atomic transactions, you need these special interfaces. Well, okay, let's say we've done that. We put a wrapper around STDQ to provide that interface and put the locks inside. Still, what's a thread-safe queue? What's a queue? Well, everybody knows what a queue is. First come in, first go out. Let's think of it for a moment in a multi-threaded context. Here's our queue. We have 2 elements coming in on 2 separate threads. We have 2 elements going out on 2 separate threads. Let's say that we actually do have an array like this inside, so we have 1 and 2. Will 1 be dequeued before 2? Okay, that's a good answer. Even better answer is, what's before? How would you know? The only way to know is to synchronize, to serialize the threads. To put the lock on both of them and actually find out, to get them to a single synchronization point and find out what they have, whether they have 1 or 2. If you didn't synchronize the threads, you can't even ask that question. The same thing on store. I'm going to enqueue 13 and 14. They are not currently enqueued, they're sitting off on the side, and I'm going to enqueue them. Which one gets enqueued first? How would you measure? Again, you would have to serialize. Very good. Is it important? Well, if you wanted a queue guarantee, it is important in order to actually have a true queue guarantee in a standard sense. In this case, what's the queue? 1 obviously came in before 2 because it's written first in the array. It has to come out first. Otherwise, it's not really a queue. What does it mean? Okay, if it's not important to you, then what does it mean for this thing to be a queue? How is it? What would you call? What's the difference between a queue and a stack? They could come out 12, 11, 10, and so on. Maybe they come out in that order. It would be more like a stack, but could they come out in that order? Well, if you have enough threads, yes, they could. Okay, so the ordering guarantee really doesn't hold with the concurrency, and it cannot hold, because even if they get pulled off of that array in the order that you think they get, the very act of the very last statement in your dequeue function, return value, that can be delayed. They may be pulled off from the array in the right order, whatever that means, but they're still inside the dequeue function. You don't get control. You don't know what order they were pulled off. The 2 dequeue functions can finish in any order they want. So, okay, we're dequeuing 1, we're dequeuing 2. Well, first of all, you would have to serialize execution to even measure. Even if you did, that return X can wait long enough for the other return X to succeed. Same for enqueue. Even if you somehow knew that you called one enqueue before the other, just because you called them in that order doesn't mean that they proceeded inside in that order. They could, the one you called first could go to sleep. Okay, so what can you really depend on from a queue in a concurrent environment? Well, if 2 values were enqueued by the same thread and they get dequeued also by the same thread, then they should come out. You could make the argument that they should come out in the right order. Well, if you have multiple threads dequeuing, you can't really have any guarantee that they'll be dequeued by 1 thread. So that's in theory it's there. In practice, it's of no use to you. If one enqueue completed before another enqueue started, then they were put in a certain order, and you can know that only if you actually know that one enqueue completed before the other started, which implies you serialize the threads. Normally you don't do that. So that guarantee is really of no use to you. So what's a concurrent queue? What guarantees does it really have? Elements usually, more or less, come out in the right order, statistically speaking. That's really what you can get. Okay? We cannot avoid this destiny. We have to embrace it. If we embrace it fully, what can we do? How about this one? An array of atomic pointers pointing to single-threaded queues. When you want to enqueue something, you get one of the pointers from that array of atomic pointers, and you do it by atomic exchange, which means you reset it to null. Now you own the queue. Now that queue is a single-threaded queue. You own it. Nobody else can touch it. You can do whatever you want. You put the value in. There is no race condition anywhere there. So let's go through it in details. How am I doing on time? Oh, excellent. Thank you. Okay, so let's go through it in details. Enqueue gets me a queue. Now, when I say get a queue, I'll show you the implementation. But it means I get exclusive ownership of one of those sub-queues. No other thread can mess with that sub-queue right now. I'm going to just enqueue into it. And then a destructor of that getQueue object is going to relinquish my exclusive ownership. What's dequeue? Again, I'm going to get exclusive ownership of one of those queues. I'm going to check if it's empty. Again, remember, my interface has to support that atomic transaction of dequeuing. So in an atomic transaction, I have to return the element if it's there, or return some kind of flag if it's not there. So I'm going to check if the queue is empty. If it's not empty, I'm going to dequeue. And I'm going to relinquish my exclusive ownership. So let's look at this getQueue. What does it do? Well, the constructor takes exclusive ownership of one of the single-threaded queues. We have this array of atomic pointers. We're just looping over the array until we find one, and we're trying to atomically exchange it with null. If we get back null, it means somebody already atomically exchanged it with null before us. Keep moving. If you get back a non-null, now it's null. That's what atomic exchange does. And you own the queue, a return. Well, what happens if you reach all the way through the array? Either you keep looping until you get something, or you exit and you return a failure. That depends on the application requirements. Whether you can, within the application context, you can basically support how it would be reported to the caller is, I failed to do the operation on the queue that you asked me to do. Now, which operation was it? It could be enqueue, could be dequeue. If you fail to do dequeue, then the answer is the queue appears to be empty right now. Well, you're in a multi-threaded context, things are getting added all the time. Appears to be empty right now doesn't mean that it's going to stay empty. So that's okay, that's valid. Just remember that there is your view in a concurrent environment, your view of what happens simultaneously is kind of fuzzy. The only things that are really happening simultaneously is between the two locks. If one lock is here, the other lock is here, everything between them is simultaneous. You can't distinguish on a more fine granularity. What happens if you're trying to enqueue? Well, enqueue just failed because you couldn't get an ownership of a queue. Is that okay or not? Depends on the application. If it's okay, fine, enqueue failed, you deal with it somehow. If not, you would have to just loop again until finally it succeeds. Eventually it'll get there. Okay, destructor is even easier. Destructor has to relinquish the, I'm sorry, this is the enqueue. Oops, sorry. Okay, so enqueue, this is the enqueue that can fail. GetQueue went once over the array, maybe went twice over the array, however you coded it, couldn't get the exclusive ownership of the queue, returned null, your enqueue now failed. I changed the interface of the enqueue. If you see, I added the bool return value instead of void. So your enqueue now failed. Okay, when would this be valid? Well, let's say back to our producer-consumer models. We have producers that enqueue, we have consumers that dequeue. What does it mean if enqueues are starting to fail a lot? It means that I'm producing so fast that consumers cannot keep up. What would be a corrective action? Well, one valid corrective action would be for the producer thread to temporarily become consumer. So if enqueue failed, become a consumer on this thread, and then try to enqueue again sometime later. You get some kind of load balancing between producers and consumers this way. Always works? No. In a particular application? Could be. Yeah?
Is it possible that the failure happens for exactly the opposite reason? That your producer fails because it's the consumers who are holding the queues and maybe pulling from them? In which case, the queue isn't full, it might need to be closed.
Okay, if producer fails because all consumers are owning, they will, so the consumers will run out basically if this happens, and eventually, they'll start letting go. Now you could.
Not if they keep looking for more work.
Well, what you have to make sure that there is no inherent bias toward one or the other. Then, and how do you make sure there is no inherent bias? There are several ways. I'll talk a little bit about that later. You can, so, in theory, arbitrary long delay can happen. You can mitigate that by smart strategies of how you start looking, and I'll talk about that in a moment. So take advantage again of specific requirements. Well, the destructor is easy. The destructor is unconditional. You just relinquish the ownership of the queue with a release store. You put back the old value. Somebody else can get it now. Well, dequeue fails if the queue is empty. Dequeue can also fail if it currently cannot acquire exclusive ownership. That's okay. If you are currently, if the queue is in flux, you may get this answer, it's right now, it's empty. You try again, it may not be empty. The only thing that the only guarantee that you really, is Michael?
Yeah, the mic isn't working when you're standing over there.
It means that, okay, so only this mic works then. All right, okay, so this mic stopped working. Okay, so if you adding and removing elements, you can get a temporary failure on dequeue. That's in general okay. It just means that according to the view of this thread, at this very moment, the queue was empty. That's okay. The view of this thread is a subset of the real world when everything is changing dynamically. Now, the only guarantee you need is eventually, if you stop adding things to the queue, eventually they all have to be dequeued, and you have that. If you want a little more reliable dequeue, you can make it so getQueue doesn't just return any queue, it could get exclusive ownership of it, tries to find a non-empty queue. If it gets exclusive ownership and that queue is empty, it puts the ownership right back in and goes to try to find the next one, and maybe that one is not empty. Of course, you don't know that there is a non-empty queue, so you have to stop that at some point, but you can do a full loop, for example, before you stop. The alternative is you can have a global count of elements in the queue. Now, that global count will not be updated exactly synchronously with the actual elements in the queue, but you can make it pessimistic. You can make it so if the count says I have something, I have something. If the count says I don't, maybe I still have something. Now, that count will be a second shared variable. You have to measure whether it's worth doing it. In the benchmarks I did, in my case, it was worth doing it with the caveat on the machines that I measured. And the results were actually somewhat different between Sandy Bridge, for example, and Haswell. And for the loads, for the mix of enqueues and dequeues that I was using as a test load.
Question?
Yes?
Any guesses as to why are the results different between Haswell and Sandy Bridge?
Well, not just Haswell and Sandy Bridge. Okay, if you want, Nehalem and Westmere, they all had different results. It's an interplay between how fast the atomic instructions are, how fast the cache updates are, how fast the memory bus.
But
the memory bus is, how close you are. Remember, when we're doing these test flows, we're basically enqueuing and dequeuing these little objects all the time. Well, in my case, they were little. If they were big, would be different results possibly. But they were little objects, so we're reading and writing memory pretty extensively. So speed of memory bus, speed of individual atomic instructions, speed of, if I want this cache line to be globally, if I want the cache coherence to be reestablished, how fast is that? Different ratios of these speeds on different CPUs.
So the microarchitectural.
Sorry?
So the microarchitectural.
You get different results, not just on different CPUs, but like, we have a machine with like 2 sockets and 8 sockets. 8 sockets is the NUMA machine, the hardware that actually does the coherency between all 8 sockets. It sits off on the motherboard, really complex, relatively slow, totally different behavior. Okay, so now, how do I avoid kind of false contention, and also how do I make it faster in general? Well,
Question, just a clarification.
Yep.
This whole thing is predicated on accepting slightly improper queuing behavior, right?
Yes, however, what I was arguing before is no matter what you do, you will, in a concurrent environment, you will have slightly improper queuing behavior.
Yeah, just double checking that we were taking that.
Yes, my argument was that in a concurrent environment, you always have slightly improper queuing behavior. The difference between this one and the traditional one is how likely are you to see out of order elements coming out. Yes, this is more likely. In practice, this is more likely. But neither is absolute. If your program requires absolute ordering to be correct, your program is incorrect. Yes, please.
Yeah, so just to see if I understand what you're proposing here. So you say in order to get some performance benefits as opposed to using just the traditional locks, you're willing to have some incorrect or partially incorrect behavior?
It's a little, well, I'm willing to have partially incorrect behavior more often than I could have had with the locks. First, I argued that you cannot have a fully correct queue behavior, at least not in any way that actually matters to you if you didn't, I'm assuming you didn't fully serialize your threads, because otherwise what's the point of concurrent program? If you didn't fully serialize your threads, the question of 2 elements came out, which one came out first, you can't even verify that. So your program has to live with that uncertainty and give you correct results. Anyway, now what I'm saying next is, okay, the program has to deal with the situation that once in a billion times they come out of order, which means it has to be correct. Okay, what if not once in a billion times, but once in 1,000 times? It's not a difference of behavior; it's a difference of how often. Okay, if you can live with once in 1,000 times, maybe instead of once in a billion times. Let's take advantage of that for performance. Okay, any other questions? Sorry, lighter than my eyes. Oh, yeah.
Yeah, I think that behavior of accepting things out of order would like to, consider that the elements of the queue represent tasks, okay? And I queue up, let's say, 3 tasks, and I know in which order the program defines most in which order they're.
What do you mean when you say you know in which order? What do you mean by that? You know in which order you called the enqueues.
Yes.
You don't know in which order they committed the elements into the array. You don't know that even with a traditional log-based queue. If
Okay, so let's imagine that they are enqueued serially, okay? And I have 2 worker threads. And the first 2 jobs will be blocking, and the third will unblock those 2 previous jobs. You cannot guarantee the forward progress with that queue.
I couldn't guarantee it even before, because the thing that you enqueued last and the one that you're waiting on could go first. See, you're pulling the tasks off the queue by multiple worker threads, but you're pulling them off the queue and then you're starting them. You pull them off the queue in the order you think you did. You pull the first one, then the second one, and the third one, and then you go to do the next execution, which is a jump to start. And the scheduler comes in and says, suspend this thread, this one a go. the last one, the one that was dequeued last, starts running its task first. Perfectly valid.
Yes.
So you already have this out of order problem.
So what will happen is that the last one will run, perhaps it will run first, fine.
And you will have a deadlock, yes. If you're using a concurrent queue for task scheduler in this manner, you will have, and the tasks wait on each other, you will sooner or later have a deadlock. The only difference between the one that I'm describing now and the like spin lock wrapped STD queue, for example, is how often. But the deadlock is possible in both cases. It's just the only difference is how often. On the assumption that you don't like deadlocks even rarely, you can't do it. You cannot have that dependence. If you need to have that, if tasks in a concurrent queue can wait on each other, you have to basically do like a work stealing. You have to relinquish the task that is waiting, put it back in, and try to get another one, which is a fairly difficult implementation. But you can't do it with just a plain queue because you never have that guarantee. Now, like if you have only 2 threads dequeuing and you know that you have like 2 tasks coming out and the third task is waiting, yeah, for this case, you may have this artificial guarantee. But then if you have 3 threads, you add the third thread's dequeuing, suddenly now all bets are off. You can have 2 threads blocked and the third one waiting.
It's actually worse than you're saying. There was a paper, how concurrent is your concurrent FIFO queue, or how FIFO is your concurrent FIFO queue, published a few years ago, where they actually got better ordering with the out-of-order queues than with the in-order queues. Measure from the client is actually seeing what's going on.
Well, but they didn't, see, the important point is you don't get absolute ordering.
Well, they did, but they got better ordering with the weakly ordered queues than with the strongly ordered queues.
I can believe that, but you know, the important difference from the correctness point of view is you have absolute order or you don't. Because like in the example that was given, the tasks waiting on each other. If you don't have absolute order, sooner or later you will deadlock. The only question is how soon.
If you're in a concurrent program that you require absolute order from your queue, you're done.
Exactly. Now, having realized that, I might as well take advantage of it. Oh, okay, I'm sorry. There was a gentleman made a reference to the paper saying that. Sorry. Sorry, made a reference to the paper saying that in the paper they measured the weakly ordered queue, which is, I guess, similar to what I'm showing here, versus a traditional strongly ordered queue where inside there is a true array and locks or some sort of lock-free synchronization guards inputs and outputs, and they found that statistically weakly ordered queue actually provided more in ordered pairs or whatever they were, ordered sequences than the nominally strongly ordered queue. Now, I can believe that. I don't think it's necessarily or always the case. May depend on the hardware, may depend on the exact nature of the strongly ordered versus weakly ordered queue. I have this, this one, the one I'm talking about. I have implemented this one. I use it precisely for scheduling tasks. I use it as a basis of my thread pool. It's faster than any other, like I tried several other lock-free queues with various limiting assumptions. I could never get anywhere close to the performance of this one. But yes, tasks cannot wait. The only task that can wait on each other, the task that started, can enqueue something else. And that, will happen later. Okay, so so this is actually the last. I'll give them 1 second. Take every advantage of practical limitations. Oh, okay, sorry, not the last one. So I'll take a question.
This may be the most chaotic question, but why did you use the queue at all? Because from my point of view,
That's a good. Okay, so if you have a queue in a concurrent environment and you use it long enough, in theory, there will every once in a while they'll come out in an order as if it was a stack. Yes, so it's statistical, and they mostly come out in the right order. So it's, your algorithm is basically faster if they come out in more or less the right order. That's why you do it. Okay, one more thing. Just okay, this is the last item, because yeah, I promised you to talk about double check locking. So, and I haven't yet. Well, I haven't talked the second time about double check locking. First check, second check. We did the first one. This was the second. So what happens when the queue is full? Well, maybe enqueue fails. But what if we want, let's say, we don't want enqueue to just fail. We want to add number of worker threads so we can run it faster. Well, you would have to rejigger this entire array of your atomic pointers, create a couple more single-threaded queues. You have to do a lot of changes to the state. Very hard to do safely, almost impossible to do lock-free. Well, it doesn't happen often. We have a problem that is very unusual and very hard to do in a multi-threaded environment. Remember the generic double-check locking pattern. That's what it's for. So what are we going to do? We'll have a global wait semaphore of some sort. If the wait flag is not set, everything proceeds normally. If the wait flag is set, we have a total system-wide lock. It means that somebody wants to do one of those global reshuffles. If the wait flag is set, we go and acquire this global system-wide lock. Now, some of your worker threads will get to the global lock first, and they'll lock it, do their job, and unlock it. That's okay. That's just the current workload being flushed out of the system. Eventually, the thread that is actually trying to do the reshuffle will succeed in acquiring the lock, at which point everything halts. That's okay, as long as it doesn't happen very often. That's the double-check locking pattern reborn. Most of the time, there are no locks. You just check the wait flag. Nobody wants you to wait. You keep going. Very rarely, you see that the wait flag is raised, which may be a false flag or not. But in order to tell the difference, you have to take that global lock. And if you get to it first, you go complete your task. If you don't get it, okay, all your reader threads, all your writer threads that didn't get the lock are sitting there waiting on that global lock while the reshuffling is going on. So, not only take advantage of practical limitations, separate special cases, rare, complex cases, into separate handling and use double-check lock pattern to handle them. Don't try to make something that runs once in an hour lock-free. Just make the check lock-free, and then if the check fails, once in an hour you get a lock. Again, real-time system maybe not applicable. In many applications it is. Okay, I think I skipped a slide that was answering a question from there. Okay, so performance tweaks. So there was a question there about, like, basically, can you get stuck hammering at null pointers? There are various performance tweaks you can do to make it both faster and less likely to get stuck in a false contention state. For example, for performance, false sharing. Is it better to have each atomic pointer in that atomic pointer array on its own cache line? Pad by 64, on x86 64 bytes, so pad the atomic pointer to 64 bytes. You have to measure. In my measurements, it didn't make any statistically significant difference, although I did find several interesting compiler bugs while trying to do that. For example, I discovered a compiler on which you can take a 72-byte data member and shove it into a 64-byte object, and the compiler is okay with that. And yeah, the resulting object is 64 bytes. Okay, when you have multiple threads starting to seek through that array of atomic pointers. Should you start always from 0? Should you start from the last slot you looked at? Or should you have a round robin? The first state starts from 0, the second thread starts from 1, and so on. You have to measure. There is a price for each of, well, obviously if you start from 0, they all hit the first, the 0 slot at the same time, so that's bad. In order to start from a thread-specific slot, you have to have this thread local index. You have to have a thread local variable. It's not very expensive, but it's not free to have a thread local counter. In order to have a next slot, you have this globally shared counter between all threads, which tells you what the last slot you used was, and that one is also shared between all threads. In my experiments, thread local, the first thread starts from 0, the second thread starts from 1, and so on, and modulo if you have more threads than elements in the array, modulo the size of the array, that was the fastest.
Is that really 40 microseconds or is that 40 nanoseconds?
Yep, 40 nanoseconds, you're right. Sorry, it's a typo, 40 nanoseconds. Yeah. 40 nanoseconds, which is about something to the tune of 10 instructions, 10 to 20 instructions. Again, in my measurements, may depend on the load, may depend on the hardware, but these are the things you can play with to see what gives you, you would probably have less chances of false contention if every thread has its own starting position. So that may save you from both false contention and give you overall better performance. In my case, it did. Okay, so that was really the last thing. I'm sorry I skipped that slide when I was answering question.
Do you write back that thread local? In other words, is it every time in starts from the same location, or do you write back?
No, every thread starts from, so this is the thread number 0, it will always start from 0 slot. This is the thread number 1, it will always start from the first slot, and so on. So no, I don't, you mean within the thread like if this thread started from 0 but succeeded on 3, that thread next time starts from 3. Yeah, I tried that and it didn't make any difference. So it was simpler to basically have that thread local being read-only. It's initialized when the thread had started, and after that it's read-only. In my case, you will discover that these measurements are fairly noisy. So you can try to do a micro benchmark where you're just overstressing that one data structure with multiple threads. It's not always a perfect approximation to how it behaves in a real system, especially if the real system is significantly memory bound, because you may discover that somebody else is saturating a memory bus. So there is a lot of noise in these measurements. So you have to have really pretty significant effect in order to observe it reliably. Like 5% difference you probably won't be able to see. Okay, questions please.
Why not randomize it? Why not randomize the starting position of each thread when it goes into the array of atomic points?
What difference would it make? I mean, which thread starts is random, and it's, there is no magic about this is the first thread, this is the second thread. It's just the order in which they were fired up. After they were started, the one that goes for the dequeue next is basically whichever one completed it. So it's the last dequeue. So they are randomized.
On every access, every time you're going to dequeue something, where you start the array, generate a random starting position, but ask requests. How long does it take you to generate a random number? Yeah.
Well, there is a penalty for generating random number. And you already have a random. If you look at which element of the array will be accessed next, that is already random, because which one of the threads is going to ask for its element next is entirely random. I'm saying the 0th thread goes for 0th element, first thread goes for first element. Well, what's a 0th thread? It's just the one I created first. after they're running, there is no difference between 0th thread and 1st thread. Whichever one is ready to dequeue goes and grabs its element. So
if you do that, don't all the threads end up ending on one thing? Even if you start them, if you have 10 pointers and you have 10 threads and they all start, first thread and first element, second thread, second element.
well, if that's all they do, then they, in an ideal case, they basically, the first thread gets the first element, the second thread gets the second element, and they're both happy. It's only when you run out of stuff and you have to look into somebody else's. You have a question or comment?
Question. Did you try going the other direction? Subtraction as well as increment?
No. I mean, you mean as a global change, I don't think it would make.
Well, like half the threads go one way and half the
Oh.
threads go the other.
I haven't. No, I haven't. Now it's a round robin, so half of them are in the end, half of them are rolled over and going at the beginning. But yeah, you could do that. I have not tried that.
I'm not quite sure whether that would have any difference.
I don't know. I don't know. That's something I can easily try. So yeah, I have not tried that.
If your argument from before stays, it's random, and you get the decide this number of threads.
It's still going to be random. You're stressing the prefetcher slightly differently. So I don't know. It may make some difference. It would have to be measured. I can't intuit the answer to that question. Question? Yes.
It seems to me that this problem is unique to you, to be common from any data
Absolutely. Well, okay. The problem isn't unique to queues. Now, the problem applies to any. The problem, as stated, applies basically to any data structure that has order of things coming in, coming out. Like if you have data structure with internal order, like a tree, that's still valid. But order of things coming in and coming out, yeah, it applies to any data structure like that. I only have 2 hours, and there are many data structures. Yes.
Have you considered using sticky queues for producers? It seems to make sense to assume ordering of a single producer. Considering single producers to local order space, I would assume that the ordering will be
Okay, if you have a single producer thread, there are a lot of, you actually don't need this weakly ordered queue. Well, first of all, in order for you to verify that assumption, you have to make sure that they're being taken out by the same thread. If 2 elements were enqueued by one producer but got you could. You have to ask yourself this question. If this assumption was violated in my application, would I notice? And in all the applications for which I have written it, the answer is no, because I don't have enough logs to actually establish the time synchronicity. I wouldn't be able to measure whether that stickiness really held or not. If I told you that, yes, it's sticky, it guarantees this order, but in reality it doesn't, would you be able to catch me? In all of my applications, the answer is no, I wouldn't be able to catch you. I don't have enough synchronization on threads. I don't have any guarantee that the 2 elements will come out on the same thread. I don't have enough synchronization between threads. I would not be able to catch a lie. Of course, it's possible to test for it, but see, the point is you have your specific application. You're not writing application specifically to catch the queue at lying what it's doing. You have an application where you're doing whatever you need to do. In that application, if I lied to you about stickiness, would you notice? The answer may be yes. You may have an application in which you would notice that I'm lying, that I'm telling you that it's sticky and really it reorders even within the same producer. In that case, this mechanism would not work for you. You have to provide additional guarantees.
I guess my question would be, have you tested queue and if so,
I have not had, as I said, in all of my applications, I wouldn't be able to detect, within the application itself, I would not be able to detect that I'm lying about stickiness. So it didn't make any difference. That's why I haven't even tried to make it sticky. You can make it sticky, you can use this design with some variants to make it sticky, or you can use the traditional queue also to make it sticky. You have to carry a little more state, like you have to carry some thread local state to make that happen. You would only do this if it actually mattered, which is if the observable results of your application differed depending on whether this guarantee is provided or not. In my case, the answer is the observable results do not differ, except maybe in a statistical sense, which I didn't care about. Yes, please, question.
Okay, first off, the spin lock you showed, didn't that also potentially deadlock because you did not yield?
Okay. So the true deadlock, in a sense, an actual classic deadlock, means you're actually hard locked. You're waiting on two locks. You can deadlock with a spin lock if you have two spin locks and one thread is waiting on first one, the other one on second, and they try to cross wait. So in this regard, it's no different from a mutex. Now your question, I think what your question is really
4 threads, 2 cores.
Is if basically what I think your question boils down to, busy waiting is dangerous. Once you start spinning, the scheduler doesn't readily give up so you could have it's not really a deadlock in a sense, it's a scheduling anomaly. If everybody else gives up that spin lock, eventually you will get it. So in this sense, it's not a deadlock. You will never stay forever deadlocked on a thread where everybody else have given up that lock and went on. Eventually, you will get the updated value. Now, in practice, you have to put. It depends on the scheduler. So I didn't want to talk about the scheduler, but in practice, you have to put some kind of context interrupt there. On Linux, you can put either schedule yield, or you can put a call to nanosleep. And you have to test which one works better for you. On my systems, which is Red Hat 5 and 6, I found that nanosleep works slightly better than schedule yield. They both work. The question is what total throughput you get if you're trying to basically, if you're so heavily congested that you're spinning a lot of spin locks. If you're rarely congested, it doesn't matter. If you're heavily congested, I found that nanosleep works a little better. But I've seen people who use schedule yield and claim that that worked better. Yes, so in reality, if you're basically busy waiting on a variable and you never do a context interrupt, after a while, at least on Linux kernels, you get into the strange state where you can spin for a while, even though nobody is actually blocking you. Just the scheduler doesn't let you go. You have to do basically context switch. It's correct. It's one of those. I told you it's precise, but not. It's accurate, but not precise. It's one of those things I swept under the rug. Yes.
I have just one question out of curiosity. So you mentioned at some point that we should think about economic operations and transactions, and that kind of leads to my question: can the transaction memory support paths? So things like X begin, X end, or X exit, are they applicable to any of that, or is it completely different?
Well, first of all, they have been rolled back. The question is about transactional memory, and can you use transactional? If you had transactional memory on Haswell, which was kind of there until it wasn't, if you had that, would you be able to basically use it for this? You would be able to make it run faster. There is more to it than memory, but you would definitely be able to. I didn't see exactly what they provided because by the time I was ready to start working on it, they took it away. So I don't know if you would be able to completely get rid of the locks or what, but you would be able to basically have some kind of memory transactions.
I mean, from my understanding, basically you have those two operations, X begin and X end, and if you don't commit, you continue the transaction before X end,
then the whole thing, basically, so your memory is either all of these memory updates succeed, or the hardware automatically vanishes them for you as if they never happened. Yes, so that would essentially elide some of the locks or some of the undos, explicit undos that would allow elision of some of those explicit undos. And you still have to test for it and know what, because if it was undone, you have to recompute. And somebody has to compute it, so you have to test for it, but it would allow you to basically not worry about undos. Not do the undos yourself. I think we're out of time, but you can come up to me and